to reasoning and kind of finish up a grab bag of topics that we haven't had a chance to cover. And then we'll be moving on. We only have a few lectures left. So just some of the logistics. Grades for homework 1, we're almost done. Sorry for how slow it's been. We'll release project info as well. It sounds like folks are forming groups already, which is good. And for presentations, go ahead and submit your proposals. I've heard from a bunch of you. This is what I meant by we only have a few classes left. So today's topics, multimodal models, which we'll kind of get started with today. Scaling laws, diffusion models, so kind of a bunch of other areas. And then finally, this kind of, I don't know, whatever other things we can fit into the last lecture. And based on the number of folks coming, it looks like, yeah, people see that the end is in sight. For all the student presentations, I will ask everyone in the class to come. That's, we're not going to record them. It's good if everybody participates. Cool. Questions about logistics? Great. OK, so here's what we'll cover today. We'll kind of get back to reasoning. Really, so far, we've talked about reasoning from 2 points of view. One was this chain of thought idea. And that was one of our inference time improvements. So we'll get back to talking about that. We'll try to understand it from a new point of view. We'll see it as kind of an early instance of what's called test time scaling. So far, whenever we talk about scaling, we've talked about scaling from the training point of view. Get a bigger model, train on more data, et cetera. Now we'll talk about how we scale up how much inference time compute we do. And of course, chain of thought was kind of doing that. It was saying do all this intermediate stuff instead of just predicting a final answer. So really, that's the key to reasoning. And we'll try to understand how that works. And we'll even see some ways that we have to incorporate reasoning into pre-training as well. Afterwards, we'll talk about where we get the signal for reasoning and more broadly. So we'll talk about verifiers and rubrics. We very briefly saw verifiers when we did RL with verifiers. But of course, it's a much broader area. And we'll talk about some of the principles. And then we'll try to extend these things to multimodal cases. Like so far, all our reasoning has been, here is a problem that I can describe in text. There has been no other kind of modality involved. Of course, what we really like to do is to have models that can reason over images and video and whatever other kinds of data you provide. We'll very briefly talk about a couple of examples for how we do that. And of course, how we evaluate, which always goes with this. All right, so let's jump in for the first part. Right? So we've seen a few approaches for trying to get our models to do something that we call reasoning. And really, this is going to be something that we can do kind of at every stage. So we said that if we're doing it with a model that's been pre-trained, and we're not, in fact, doing any training at all, it's just a fixed model, then at inference time, we have to do one of these tricks, like chain of thought. And this can be, think step by step. It can be in-context learning with worked-out examples. It can be other things, right? It can be, hey, here's a textbook that has a bunch of things to do. Keep that in mind as you try to solve a problem. And then we saw there's other ways that we can do this as well. We can try to improve our models, right, in such a way that they're better at reasoning. And we can do that with either SFT, so literally take a bunch of problems and go ahead and run supervised fine-tuning on them, or we can do it with RL. And we saw that RL tends to actually give a lot of improvements. And the other nice thing about RL was we don't have to have worked-out solutions. We just need the correct answer. If we can verify it, then we can do RL on those kinds of problems. OK, so these are pretty powerful. We can even start to think about how do we improve models during pre-training to also force them to be better at reasoning in general. OK, so all these things, the one thing that we'll need is some kind of signal, right? We want our model to have some way of figuring out, is it correct, is it incorrect? And there's lots of choices that we can have for it. So those choices could be a correct solution. They could be some other model that tells us some information. They could be a reward. There's lots of different things they could be. It could even be the original model itself being asked to think more, or being asked to reflect over its current answer and figure out what works and what doesn't. So this is kind of what you want to be thinking about for reasoning. Where do you insert it? What part of training? What part of inference time? And how do you get any kind of information about whether you're right or wrong and what you should do? And there's now like 10,000 papers on this stuff, but they always tackle one or the other or both of these things. Cool. Questions about this stuff? All right, let's jump in. The first part is just really review, right? So we did this chain of thought thing, and it was very, very, very simple. It doesn't involve changing the model at all inference time. And in its simplest form, it just encourages the model to go ahead and actually do some reasoning. Take a problem, try to break it down, try to go step by step to solve it. And that does work, at least a lot of the time. But how well it works is, of course, a function of a bunch of other things. How hard are the problems? How big and how powerful is the model? What can it do to actually do this reasoning instead of just predicting an answer? And so you can see some of the results from the paper itself. If you look at the dashed line, that's sort of what you could do if you train a specialized model, not a large language model or a foundation model, but a specialized model that's meant to be good at these problems specifically. Right, so this is what we're trying to essentially replace with large language models, which are much more general. So if we can get to where that dashed line is, that's good. The other two lines here are blue, which is chain of thought, and this black line, which is just standard prompting with no chain of thought. That means you're going to predict an answer directly. There's no running the problem or breaking it down or anything. So you can see here that sometimes we can catch up, depending on how powerful the model is, or potentially even improve on the supervised baseline. This paper is written by Google, so unsurprisingly, their Palm models, which is what they had at the time, are the ones that beat the supervised baseline the most. And as you can see, chain of thought tends to do better than just regular prompting, but it's also dependent on having problems that it can work with. So GSM-8K, which is very simple grade school math problems, do require simple reasoning, and therefore you're getting some boost over there. And in fact, several models get a pretty big boost. But other ones, perhaps not as much. Maybe you get a much smaller boost, maybe you don't get anything at all. And the other thing to note, of course, is the benefits are really for larger models. Your base model needs some capacity to do this stuff. Even if you do chain of thought, there's no guarantee it does anything if your model size is not big enough, which is all the points to the left of these graphs. Okay, so this was the story as of like 2 to 3 years ago at this point. There's some downsides, of course, for chain of thought, even though it was a big step forward. Right? You're always generating this one single linear path of reasoning. If the model makes a mistake when it goes from step A to step B, you cannot recover from that mistake, right? There's just nothing you can do in that case. So that's a pretty big downside, and that's really what we want to get rid of as much as possible. We have no chance of really exploring a broader solution space. As soon as we take a step, we're committed to it. We cannot backtrack. We cannot say, here's 3 steps I should investigate. It's always I go forward, and whatever I get to, that's what it is. Okay, so this is the biggest downside. And of course, it can only help in some areas, unfortunately. But it's still kind of a nice step forward because you can think of it as an early form of this test time scaling thing I mentioned. So what are we really doing when we do chain of thought? We're basically trading off the number of tokens generated versus our probability of producing a correct solution. Right? So direct prompting uses far fewer tokens, so it's way more efficient, but it's just less likely to get the correct answer. And as we try to get more and more tokens, our chances of getting the correct answer go up. Everybody agree with that? Now, chain of thought does not have some direct control over how many tokens we get to use. It's not like I can say, hey, I want to invest 2,000 tokens, right? And I want to use them as efficiently as I can to increase my probability of getting it right. However, it's something like that, right? The model will decide on its own how to break down the problem, how many steps to take, and it will certainly use up more tokens than if we just ask for a direct answer. Okay, so what's one cheap way I can control the amount of tokens I use? Go for it.
I just have a question about chain of thought specifically.
Let's ask first, yeah. Go for it.
How many parameters does it actually start to manifest? So like when does the telling it to think step by step cause it to exist?
Well, the original story, which is not believed anymore, is that there's some weird transition around 10 billion parameters. And before then, everything is very hard. You don't get any of these nice behaviors. There's no really solid ICL. There's no great chain of thought, et cetera. But beyond 10 billion, suddenly all these things emerge. But then it turns out, we can use much smaller models today. And there are models that are like 500 million parameters that can do chain of thought. However, there's tricks to do this, right? So for example, these models are distilled from larger models, so they see very specialized data, et cetera. But it doesn't seem like there's a very obvious threshold. Yeah, that's a good question. OK, so let's get back to my question. If you do want to control the number of tokens you use, what is one way you could do that? Go for it.
We have a hard limit on how many times it needs to do step by step. For example, if it goes through a problem, just do it.
Yes, we can do that. We'll actually see a paper that does exactly that in just a few seconds. What is an even simpler way than that? Where I don't directly do anything to any single output generation. And we've seen this before also. All right, I'll give you the answer. One thing we can do is just to ask our question multiple times and collect multiple responses, right? That's entirely up to us. If I say I want to use 1,000 tokens, and my typical answer is 100 tokens, then I can just run 10 times. Not every generation will have an equal number of tokens, but roughly speaking, I'll be able to do that. And that's really going to be a great deal of what test time scaling amounts to, is just running the same prompt and sampling multiple responses. Of course, we want these to be different, so we have to think about things like temperature. But that's going to be the way that we generally control what we're doing. It'll be much more easy to do this compared to directly controlling any single generation itself. Cool. All right, everybody okay with chain of thought? Any other questions about it? Yeah.
I was kind of wondering in the inference and the backend side, if we do majority vote by test time scaling, is it just like they feed forward the necessary part, but then the actual output, they just do it in parallel with different computers?
Depends. Usually no. You just collect multiple responses, and then you go ahead and look at all the responses and run majority vote. But if you have compute to run in parallel, then sure, right? There's nothing wrong with that. I don't think that's what people typically do when they run these data sets, but yeah. So keep in mind that all this stuff is not like built into the model by default. This is just something you put on top, so you get to control whether you're parallelizing or if it's sequential. Awesome. Other questions? All right, so we saw chain of thought, and then there were all of these variations on it as well. And this is really what people did for a while. They tried to fix up the issues with chain of thought that we just saw, like the fact that I get to control one single path and that's it. And they came up with these fairly sophisticated solutions. The one that we talked a bit about is called tree of thoughts, but there's actually a ton of these guys. The nice thing about tree of thoughts is that it kind of directly tackles this problem of, oh, I can't backtrack, I can't explore multiple paths, and I can only look at one single path. And the way to think about this stuff is the picture that we saw already from their paper, right? So standard prompting is this guy. One input directly produce the output. And then chain of thought is this guy over here. There's an input and a bunch of steps that are intermediate, and then there's an output. And then the standard thing that you can do, which we just mentioned with majority vote, is this guy over here, which is to say I'm going to sample a bunch of different paths. So this is also another way of doing test time scaling. It's the one that we mentioned, where we get to control how many of these there are. And then we combine them by looking at the end. We look at all the outputs, and we take the most popular output. And they call this self-consistency, but it's really just majority vote. There's nothing special here. OK, so this solves one problem, which is that I can explore some more. I am not stuck with one single path. But unfortunately, it doesn't solve our other problems, which is, well, I don't get to backtrack. I don't get to control how I explore, et cetera. All I'm doing is sampling paths. And if I find one that works, well, hopefully a majority that actually work, good. Otherwise, I'm stuck. So tree of thoughts is meant to sort of solve that problem. It basically says, hey, I'm actually going to use the language model, not just to sample paths. I'll use it to sample individual steps conditioned on previous steps. And I'll do that not just as part of a path, but kind of at each step to create a bigger graph. So I'll start with my input, and I'll say, OK, well, what are the first step possibilities? Give me a bunch of different ones. And that creates 3 of these children. But those things are created in parallel, right? So I have 3 different candidate first steps that I could take. And for each of those guys, I could go generate multiple candidate next steps. Now, of course, I get to control how many of these children I generate. I get to control things like how many of these things should I create before I start looking for a solution, et cetera. But it does give me this larger graph that I can work with. And now I can do anything I want, including backtracking, right? I can say things like, oh, I've looked through this path, but it doesn't look so good. Go back up, continue down a different path, and so forth. The only downside of an approach like this is basically that it's an external harness that isn't inside the LLM itself. I've now reduced the model to just generating candidate thoughts. And I have to do everything else. All of it is up to me. And really, that results in I have to know a lot about this problem. So I'm not really using the reasoning capabilities of the model so much. I'm using my own reasoning capabilities. and the model is just a small tool in there. And similarly, if I want to do a good job over here, I'm going to have to generate a very large graph, right? So this is going to get expensive as well. So this is kind of the problem with these tree of thought type of solutions. I really want to make my model reason better, not sort of just use it as a piece in some larger system, which is something that I have to implement and control. OK, everybody agree with this logic? Cool, so this is kind of like what you could do up to about a year ago. And then things changed with these reasoning models that, as we saw, were designed through RLVR. So that increased their own ability to do all of this stuff. And these things are now happening within the model generation. So rather than saying, hey, I control each of these thoughts, I write them down in a big graph, the model, while producing tokens, is doing all of it internally. And it's doing it because it has access to these notions of thinking tokens, and it can figure out what to do internally as a result of these. So that's sort of the big difference. No external harness that we build. Instead, the model does it all itself during generation. And we can still run the model multiple times. We'll do exactly that. But it's much more sort of simple and internal to the model than these kinds of external harnesses. All right, everybody OK with this distinction? Go for it.
How do you control exploration in this entire thing?
How do we control?
Yeah, like as in, for a generic problem, how do you state like, this is not a good path to go down and then let's backtrack?
Use a heuristic, which is what I would do in general anyway, right? And typically that heuristic ends up being another model. And I ask that model, hey, is this particular direction, this path, is it a good one? Or of these three candidate paths, which one should I go look at first, right? So the answer is I have to know something, or some other model has to know something to help me out. Otherwise, if I have no information, I can run this process forever, right? I can create an infinite graph. Cool, other questions about this? Awesome, so let's start proceeding. We're gonna start talking more and more about models that can do all of this internally. One thing I want to also highlight is we've been treating kind of reasoning as like one sort of thing, like either you're good at reasoning or you're not. The interesting thing is models are actually fairly differently able to do different kinds of reasoning. So here's an example. You can break down reasoning into different forms. So deductive versus abductive. Deductive means you have to use all the information and kind of actually reason through it. Abductive means you have to make reasonable assumptions. This is just kind of one way of breaking down different forms of reasoning. And people have sort of studied these types of things and found that there are fairly substantial differences between how good models are on these different forms of reasoning. So these are a couple of data sets. You're seeing two columns for these two forms of reasoning, and this is the error rate. So for example, over here, deductive reasoning is much easier for models than these abductive forms. They don't make good assumptions. They can't fill in the blanks very well. And that makes things much more challenging in those scenarios. So there's lots of different ways of doing this kind of breaking down reasoning. You can also think about far more particular forms of reasoning, right? So is my model good at causal reasoning? Is my model good at temporal reasoning, et cetera? And there's fairly large gaps there as well. So very often what we're kind of stuck doing is trying to identify where models do well and where they do poorly, and then building data sets with that form of reasoning and then tuning over them. So all this stuff is not like one size fits all. I can make my model a good reasoner. It's more of this iterative process. Figure out where we don't do well, build a data set, tune on that data set. Hopefully you don't forget other things or become bad at other things, and then keep this whole process rolling. Everybody okay with what I'm saying here? So you generally should not assume that just because you have a very powerful reasoning model that will actually work on your application. If it's aligned with what the model's seen and been trained on, chances are much better. But if it's not, you're stuck kind of improving it yourself. Cool. All right, let's get back to what I mentioned in the beginning, which is test time scaling. Right? So traditional scaling here, and we'll talk about scaling laws in just a bit in the class, but the real three ingredients that everyone looked at are how big is my model? So this is how many million or billion weights do I have? How much data do I have? And again, this is very coarse pre-training data usually. So it's a question of how many trillions of tokens do I have in my training corpus? And then finally, how much compute do I have? Which is to say, how many epochs can I do over my data? Often the answer is only one or something like that. OK, so usually from scaling, I want to increase one of these quantities, get a bigger model, or get more data, or increase how much compute I have. And I hope that if I increase that one quantity, my model will perform better. Typically better in a very simple language model kind of sense, like, for example, my perplexity has improved. So now we'll see that this kind of traditional scaling, in lots of ways, it's sort of starting to reach its limits. It's getting more and more expensive, and there's diminishing returns from scaling up either the data, or how much compute I throw at things, or how big my model gets. So the next step is not really, let's make our models trillions of parameters. It's more, let's figure out how to be more clever about our model usage. So this is kind of the biggest difference between now and, let's say, 2 years ago. The expectation 2 years ago really was continuous scaling up, especially in the pre-training side. Today, very few people think that that's sort of the way to go. And instead, we're trying to think of, well, if I have some amount of compute, sure, a lot of it is dedicated to pre-training, but of what remains, I should think a lot about test time kind of compute. All right, everybody see what I mean by this? Cool. So let's go ahead and take a look. Test time scaling is just literally increase your inference compute. And that could be as simple as running the same question many different times. And it can be something more clever, like try to control how much thinking my model is doing. But either way, it's basically exactly the same thing, right? More samples / longer chains in specific ways. This is where you really want to invest more and more of your compute instead of doing bigger models. And the intuition is simple and kind of silly, right? There's this famous joke about, if I have infinitely many monkeys that are just bashing on a typewriter, eventually they'll create Shakespeare's plays, right? Those monkeys are not very intelligent. They're intelligent enough to type stuff, but if you have enough of them, you'll find whatever work of art you want in their outputs. Same basic idea here too, right? So if I have my models, they're capable of really outputting anything. I just need to try them often enough. Now, what's the point of creating smarter models? Well, the amount of time it takes to get the right answer goes down, right? I just increase my probability of getting a correct solution. And that can make a big difference. If it takes 100,000 tries on average to produce a correct solution, and I reduce that to only 1,000, that's a huge, huge, huge reduction in compute. But that's really what all reasoning is about today. Can I improve my probability of success? Can I reduce how much inference on average I have to do? All right, everybody agree with this logic? Cool. OK, so let's see a paper that really uses this idea. It's called Large Language Monkeys. This is quite a nice paper. It's exactly the notion that we talked about. We're just going to do repeated sampling. And by doing this, we'll do test time scaling. So the simplest possible form. Generate a bunch of candidate solutions. And again, 100,000, 10,000. It can be a fairly large number. And then we're going to go ahead and rank them. How do we rank them? Well, we'll take a bunch of scores. The scores will come from something. It can be a verifier. It can be a reward model. It can be one of many different things. And then we'll take the one that has the highest score from this tool. So really simple idea. Notice that we are not going to necessarily do majority vote in this case. We have more information. We have this verifier. And it permits us to do ranking. I'm not stuck just saying, hey, whatever is the most frequent answer is what I'll give. OK, everybody agree with the basic logic here? Cool. So this is kind of the most simple form of test time compute. This is also called best of n. So this is good to know about. You'll see this terminology pretty often. If I go ahead and produce n solutions, I score them and rank them and take the best one according to that score. That's what this best of n solution is. All right, so 2 key goals for this paper to study. And it really is just a paper that's studying things. One is to look at coverage, which is basically to say, hey, if I had an oracle that told me which solutions are correct, is there one solution that's correct in my outputs? So if I generate 10,000 solutions for a problem, did I cover the correct solution with these guys? So obviously, if you have low coverage, then there's not that much you can do except to get even more generations. The other is precision, which comes down basically to, hey, if there is a correct solution, can I identify it? And you can imagine that if my verifier is not very good, it might score the correct solution very low. So even though there is a correct solution, I just don't get it. It's not going to be at the top of my ranked list. So both these things are problems. That's why we want good verifiers, and we also want good generators. Everybody agree with this? Now, of course, if we have a verifier that can literally just check, right? We have the correct number answer to a problem, the verifier just says, hey, is that the solution your generation got? Then of course we have no problems at all. But most of the time we do not have that. So we'll have to do something different, and then there's a chance my verification process will also be wrong. All right, so here's the approach, right? So you have some problem. You have some generative model. This is my LLM. It generates a ton of different solutions. Some of these might be correct. Some of them might be incorrect. Usually many are going to be incorrect. Then I have a verifier. It's going to say, OK, go ahead and rank all of these solutions, give them a score, and put them in order. And then I'll take the top one. And I'm hoping that if there is a correct solution in this set, it'll get ranked really high and therefore be the produced solution. All right, so let's see some examples of what these folks found, which is pretty interesting. So the coverage depends, of course, on how hard your data set is and the kind of model that you have, which shouldn't be too shocking. So let's see some examples from the kinds of data sets that we saw, a lot of which are these agentic settings. So here's SweBench. That was the software engineering kind of benchmark that we saw before. So here's what we're doing for test time compute. We're increasing the number of samples. This is the number of generations that I'm doing. That's my x-axis. And I'm checking out the coverage, right? And this is just literally, I have an oracle. I want to see if one of my problems is going to be in there. Sorry, one of my solutions is going to be correct. And we're seeing that average over all these SweBench-like problems. And then you're seeing this blue curve over here, which is that it's increasing all the way from, I don't know, fairly low coverage to something like over half of them are correct. That make sense for everybody? Now, of course, you can compare this to saying, I'm not going to do any of this test time scaling. I'm just going to take my favorite, very powerful model, run it once, and see what happens. So those flat curves don't have any scaling. I'm not increasing the number of generations I'm doing. I'm just using a very powerful model once. And as you can see, eventually, if we keep scaling, we'll beat those guys. So that's the promise here. Even if my model isn't the best model, if I give it many chances, eventually it's going to start getting a higher percentage of the problems right compared to any fixed model. Cool. So what's the downside? Yeah, I'm paying a cost, right? So instead of using a powerful model once, I'm using a weak model, I don't know, 1,000 times, right? So I have to figure out this trade-off between, is it better for me to use a more expensive, powerful model a few times, or a much weaker model a larger number of times? And it's not trivial which of those is going to be better. And that's why we'll have to build some curves that show us what our performance cost is, right? And then we can actually think of these things in terms of things like flops. How many total operations am I doing? So a larger, more powerful model, running it once is more operations than running a cheaper model or smaller model a few times. But eventually, running the cheaper model many times will kind of overwhelm that too. So that's the thing that you want to consider here. And it's actually fairly similar if you look at a bunch of other data sets as well. So similar with math, similar with code, et cetera, et cetera. Eventually, we'll be able to actually do really well. So for this particular data set and GSM-AK, which is pretty easy, you're actually getting to 100% fairly quickly. So of course, your test time scaling curves eventually will hit that, and they don't improve any further. All right, everybody OK with this idea? And notice that it's kind of surprising, right? People often talk about the capacity of language models in the sense that, hey, there's some problems my language model just cannot do, right? This is a very common way of thinking. But really, a language model can produce any solution whatsoever. It has the ability to output any combination of symbols. The only question is, how long does it take to find it, right? How many samples do I have to take before I get to one that's actually good? So a very weak model might really take forever. And that's why I'm not really going to go ahead and use very bad models. But in the end, everything is capable of almost any problem at all. Cool, let's see some more examples of this kind of stuff. So same basic idea here too, right? So we're looking at 8B model versus 70B model. This is llama 3. And you can see basically where things start to level off in general. It also very strongly depends on the data set. And we're seeing here now things based on how many flops we're using. So we're no longer tracking directly, hey, how many generations did I get out? Because it's impossible to compare those two things for different model sizes. Instead, we're going to incorporate all of them into this flop count. And therefore, we'll see in some cases that the bigger model is better, and in some cases that the smaller model is better, right? It just depends on this product of how many operations does a generation take versus how likely are we to get the problem right. So this is all the different cases here. And you can see, for example, in this mini 2F math data set, that basically I'm for a long time actually better off using the smaller model. And then eventually in other cases, I'm actually better off using the bigger model. Right? So in the case where the bigger model is better, the weaker model is so much more unlikely that it's not worth using it. In this case, it's the opposite, right? The smaller model has pretty decent chance of finding things, and therefore it makes sense for me to use that one. All right, everybody agree with this? Yeah?
But there is no learning or feedback happening while during this process. So what is the intuition behind the performance increase of the model?
It's just the fact that I get to see more solutions, right? I'm sampling solutions. In the end, the language model is the big distribution. I get a sample from it, right? And I'm saying, hey, I'm sampling solutions. I get to look at all of them. These solutions are different. They cover different parts of the solution space. Eventually, I'll find one that's correct. That's the only intuition here. So think of this thing as like, I asked different students, try to solve this math problem. And I asked millions of people. Eventually, I'll find somebody that gets it right, even if it's a very hard problem. Same basic idea of a language model.
So there's no guarantee that the model might do well in the future, right?
If you're talking about a different problem, or do you mean like a different data set altogether?
Different data set altogether.
No guarantee, yeah. I may get lucky and have similar results, but no. But all of these curves are averaged over all of the problems in one data set. So it's not about a particular problem versus another here. Yeah?
What if, due to the nature of the LLM you're using, it just won't look at a certain part of the subspace?
It will eventually, right? So there's no sort of sequence of tokens that have exactly 0 probability of appearing in pretty much any LLM, if you see what I mean.
Sure.
It's just less likely, and that means I'll need way more generations to see that part of the space.
Yeah, okay.
All right, everybody okay with this idea? As we move to scaling laws especially, we will start thinking of everything in terms of operations, right? That's sort of the final arbiter of how good our language models are. Because I have to pay for flops, right? There's only so many of them that I can do. All of them come at some dollar cost because I need devices and I need energy to power them. So this is sort of the ultimate metric that I care about. It doesn't really matter how big my model is, because maybe a large model requires fewer generations. Maybe a small model requires many of them. But if I track flops, all that stuff is sort of transparent to me. I don't really care. I just want to minimize flops versus performance. Cool. All right, let's go ahead and answer this other question, which is about let's figure out what's going on with problems. This is what I find fairly interesting as well. What do you expect to see, especially if you don't have a very powerful verifier? So this is doing basically a bunch of different problems from GSM 8K, which is a fairly simple data set. It's not too crazy. And what it's showing basically are problems sorted essentially by coverage, right? So it's saying, hey, what percentage of the solutions that were generated out of 10,000 were correct? And here, correct means not ranked correctly by a verifier. Correct means literally by the oracle. So this is sort of giving us more information about how hard problems are. And we can sort of see there's a few problems that are really hard. And in fact, what you're seeing over there is, hey, 20%, not a very high chance of us getting it right. And then as we keep going, we get 50, 60, close to 100% of our generations are correct. So this is the interesting part. You can say, OK, well, for a data set, if I'm going to do something like majority vote, I really need many generations to come out correct. If my data set isn't like that, then things are going to be very difficult. But if my data set does have that, then things are much better. And notice that you can actually also kind of see the changes in all of these things based on how big my model is, right? So Llama 3.8b is over here. And you can see this increase. And then Llama 370b, which is a much larger model, has a much steeper increase, right? So there are far fewer problems where it's going to struggle with them. And same deal if you look at this math data set, which is actually a collection of different smaller math data sets. You're seeing kind of a very gradual increase versus one that's quite a bit faster. OK, so these are the kinds of things that you need to think about for all of our verifiers. We need to make sure that, well, the model that we're generating solutions with is good enough, but the verifier also has to be strong enough to be able to pick out these good solutions. Cool. One additional thing that we might think about is instead of just taking off-the-shelf models and hoping that they have good enough reasoning capability, that when we repeatedly sample them, we'll get a good solution. We might also think about trying to improve the models themselves. And this paper is quite nice. It's called S1. This is a very, very simple approach to trying to improve test time scaling. In other words, take a base model and modify it so that test time scaling is going to work better. Okay, and the way that they did this is basically with this very simple two-step approach. The first is that they went ahead and did some training. So you take a base model, and then you create a good data set, and then you curate the data set itself and train on that one. And this is very simple training, not RL, it's just SFT based, on something like 1,000 problems that are pretty representative. And then the second trick that you do is explicitly try to control the amount of thinking. And this one is actually a little bit more interesting. What they basically do is to say, hey, enforce some minimum number of thinking tokens for each problem. So if the model accidentally tries to do some very stupid shortcut solution that involves very few tokens, then you basically tell it, no, you should wait. In other words, continue generating tokens, continue looking at your own solution until some minimum number of tokens has been consumed. And then you also do the same thing at the other way. Instead of allowing it to go on forever and consume tons of tokens, you say, hey, you're not allowed to go past a certain maximum number of tokens. So we're controlling the minimum length of the thinking tokens and the maximum length as well. We're constraining it between two extremes. And by doing this, basically, we can kill off a lot of errors where the model sort of fought too fast and finished too early. But we're also preventing it from going overboard and thinking and getting stuck forever on some particular other problems. And this actually helps quite a bit. Now, how do you set what is the appropriate minimum and maximum? That's another kind of practical problem. You have to tune over these things as well. Okay, so this actually works quite well. This is just one example where basically if instead of you do just vanilla test time scaling, you actually use their technique, which is to say train on your data set and use this minimum and maximum, you can get much, much higher accuracy much sooner, basically. So this is what we're showing here. These are the curves. This is measuring the total number of tokens generated. So for example, I ran 100 times, and the average number of tokens per solution was 1,000. And then over here, you're saying, OK, well, the accuracy rate increases. Now it increases much faster. Why? Because basically, we're not consuming tons of tokens for some problems. We're not consuming too few tokens where the problem is going to be wrong. We're getting something kind of in the middle here. All right, everybody OK with this idea? Yeah.
So this is doing supervised fine-tuning, right? So they're matching up against an actual text when like they're trying to minimize the differences between those texts. My question is how that, like I don't understand how it's using supervised fine-tuning when they have to control the number of thinking tokens. Is it just like this is the preferable amount? Is that what they have for supervised fine-tuning?
Yeah, so all the solutions that you have in SFT are already within those bounds. But you additionally do something else, right? Which is that you do an intervention into the model. So if the model at test time, independent of training, is finishing up too few tokens, then you insert a special token yourself. And this is this wait token. And this forces the model to continue. So you do have to inject these special tokens. And of course, the termination token is literally just you stop here. That's the end.
So the control comes at inference time.
Yes.
They're training on a problem before that.
Yeah. Yeah, the training is meant to say, hey, we picked out really good problems that induce better reasoning. So go ahead and get those better abilities compared to the base model. But then they also have this additional control level. And this one, again, is meant to say, hey, problems that you're probably getting wrong because you use too few tokens, don't do that. Problems where you're getting stuck forever in some loop, for example. You're burning lots of tokens and still getting it wrong. Don't do that either. Yep.
You said they inject the wait token. Do they stop it before it emits an end token? And if so, how do they know when to stop it before the end token?
No, I think it is when the end token comes.
Okay.
That gets swapped out for this wait, and then you keep going from there.
Cool.
That's a good question. So I don't know the exact technical approach, but I think it's just literally that, right? You, like, instead of saying, hey, you're permitting this final token, stop there, you come in and reject it and put in the wait.
That makes a lot of sense.
All right, everybody OK with this? OK, so now we're starting to see larger complexity of this test time scaling space. So far, we said, hey, get more generations, right? That's been our way of doing test time scaling. Now we're saying, yeah, get more generations, but also make them have some property that we want. Make them not too short, not too long, et cetera. So indeed, there's lots of things that we can try here, and that's sort of the point of this paper. Simple tricks can give you a much steeper improvement curve. So instead of getting stuck with this very gradual increase as I compute more tokens, I can make it much faster. I can accelerate myself from whatever this is, 50% to 60% much sooner. Cool. So this actually is a very popular paper from earlier this year, and fairly simple as well. OK, so as we saw, we're now doing things at inference time. We are, of course, also doing a little bit of training, as we saw here with SFT. The last thing I want to say for this section is that we can also do things in pre-training to try to encourage reasoning as well. So normally, we don't think of pre-training as being that related to things like reasoning. We think of pre-training as just kind of getting capabilities for language and some very basic notions of whatever intelligence we have. But actually, it turns out that for pre-training as well, it does make sense to think about it. So let me show one example that I like. And this is from one of my students. But basically, so scaling laws, although they're predictive, they're very coarse typically. So the most basic form of a scaling law, we'll spend a whole lecture on this, but just very briefly, it's literally saying, hey, if I throw this much in terms of compute, data, and model size, I can predict this kind of performance. And by predict performance, I mean generically on all language modeling tasks. Well, one thing that we can do is basically make it much more specific. I can predict things like performance on reasoning. And the other thing that I can do is try to look for, depending on what kind of data I show it, what is actually the result. So instead of saying, hey, throw all the data undifferentiated, and as a function of how much of it there is, predict performance, I can now say, hey, let's compare data that is meant to be doing reasoning versus data that's doing other things like knowledge. In that case, can I see what my predictions look like? And do I see a different kind of scaling behavior? And the answer, interestingly, turns out to be yes. So you should read the next paper here. Reasoning and knowledge have fairly different scaling laws. And that has implications, right? Because depending on what my scaling law looks like, I can say things like, oh, I need a bigger model, or oh, wait, I need more data. Now, we do that generically, like we only care about undifferentiated pre-training data and just a bigger model. Now we can start thinking about that more specifically. So just as an example, though it's slightly hard to read, what this graph is really telling us basically is for reasoning, I would like to have more data. It's not that I need a bigger model. I just need to see more data points to train on. On the other hand, for knowledge, which is to say facts, relations, et cetera, what I really need is more of a big model. I don't need more data. That doesn't help me here. I like my model to be larger. Right? So I've separated two sort of forms of data, or two kinds of skills. And those two kinds of skills have different scaling law behaviors. And they tell me I should do different things, like I should get a bigger model, or I should get more data. So this is something pretty interesting. It's really telling us more information about what exactly we'd like to target with our model. And now we have to get into a more sort of fine-grained type of training, rather than just saying, OK, give me the optimal model size, amount of data, amount of compute. OK, so this will all make a bit more sense once we do our scaling laws lecture. But any questions about this? I will try to spell out next time as well exactly what this graph means. But we'll see in a little bit. Cool. All right, so let's pause there. And I can answer questions. And you guys are welcome to take a break. No questions? You guys all look tired. Is it midterms or something else?
Way to the world. Are you going to release the project information?
Yeah.
Let's see. This is where I said this is messed up. Say you're talking just enough. Because you can't really do anything if the other person doesn't know anything, right?
Yeah.
Obviously, you can't post everything. At what point do we just rag on model with rather than just, the actual knowledge themselves?
I mean, that's actually like a big goal that people have, and it's this thing that they call the cognitive core theory. I want an LLM that's, it's acting like a brain. It can reason, recall information from other sources. It doesn't really need to know much by itself. The problem is we have no way to easily get to this, right? Like when we're doing pre-training, we are getting lots of knowledge. So it's not like it's an easy way to separate knowledge from everything else, right? It'd be nice to, but we don't have like a means of doing that correctly. So that's the first problem. The second problem basically is like, it turns out that it is useful to have some knowledge, that you have like right? Like if you have zero knowledge at all, everything comes from tools or RAG or anything else, like you're somehow slower in lesson 2 of that things too. It's kind of like we tell people to learn the multiplication table, even though, of course you can use a calculator at any time, right? Same kind of idea. So that's why like there might be some challenges to accomplish this concept. But people are trying it, right? Like people are building smaller and smaller, but still good reasoning LLMs.
Yeah.
You just have to trade off like a lot of other information skills.
Right, that's what I noticed with Google's models. They don't have mixture of experts. So that's what I'm wondering is just like, do they just not, do they have a wired knowledge or do they just have knowledge and it's just stored away somewhere?
Yeah, both, right? You can have memories, additional knowledge. Or you can say, hey, I don't know how to do multiple applications. But again, the hard part is more like, can I actually get rid of knowledge, right? It's not super easy. Nothing you do will guarantee that all of your weights are used for the reasoning capabilities you want.
Yeah.
Right? Like you can't fully. We have different kinds of memories, so we don't have to do it all. We have these parametric memories that are just weights. We have things like vector databases where we can retrieve stuff that's been stored. We have, of course, just big lookup tables and things like that. So any of these things, the only question is, well, can I get that stuff and use it, right? And is it too slow? That's the other problem. Because like, if I have to like wait 10 hours, that's also not going to go. Yep. That's it. Yeah, so we will pay for it in some places, right? Maybe we'll get, and we'll have some places where my model will just about and then it didn't, right? And that's bad. But we're also going to like get rid of a bunch of places where the model was thinking forever because it was stuck somehow, right? And now we're telling it no, don't do that. So we save ourselves all those difference.
That makes sense. Okay. So you're trying to train to a reasonable range that's ideally not too short.
Exactly.
Okay, I see.
What that range should be is kind of like data depends, right? Depending on what kind of problem you're tackling, you have different versions.
Let's say large, this is also basically just time scale.
It is. All of these are also dust time scaling. Like you can think of chain of thought as the first form of dust time scaling, but it was very much sort of like directly control how long the generation is. And then sort of these other chain of thought variants are closer to just do a bunch of sampling, right? Reasoning. However, none of them was sort of like the more modern stuff is
Also, and then also, like you were saying, is information compression from the original forms of chain of thought. They all require either an LM as judge
still need your model to be good enough, right, to pull out enough correct solutions, otherwise there's nothing you can do.
Okay, that makes sense.
Yeah, so I mean, we always have ways of picking out the solution. The only question is, yeah, like if we have extra information, can we use it?
It's not interesting. I think you could like incorporate that also by the standard. Yeah. Not interesting.
All right, folks, let's keep going. So the next part I want to talk about is just a little bit more on verifiers and another kind of mechanism that we use for evaluation called rubrics. They are basically what they sound like. So for verifiers, we'll try to break it down into a few different types. So far, the verifiers we've seen are very much like, here is the correct answer. And for this particular problem, this is what you're supposed to get. Those verifiers are great because those are oracles. The downside is for many kinds of problems, we don't have them, right? I want to work on cases where there is no simple right answer, or I have no access to it, even if there is. So we'll talk about weak verifiers, which is all the cases where I don't have this kind of oracle. Then we'll talk about how we designed them, and then a little bit about these rubrics. And we'll see some examples of sort of modern large-scale evaluation data sets that do use quite a lot of rubrics. OK, so why are we doing this business about verifiers? I mean, it's for exactly the reason that we've seen so far, which is even if we're doing test time scaling, even if we're getting many generations, we still need some way of figuring out which of our generations are correct. And if we have no other way, we'll have to do these things like majority vote, where we have no extra information. But in general, that's very difficult, right? Because if I don't have a majority, then I can't really do too much. So we'll want to introduce some kind of verification tool. If I have access to an oracle that really can say, this is correct, this is not, I want to do that. But unfortunately, a lot of the times I don't. And in that case, I really want to minimize my gap to that oracle. So we saw, for example, if we use things like reward models or confidence scores or other things, we are not guaranteed to find what is the correct solution from all of our generations. And in fact, we have some examples of how big that gap can possibly be. What you're seeing over here is that blue curve is the oracle. So it's saying, hey, I have some way of seeing whether any solution is correct. And therefore, if there is a single correct solution in my generations, I'm good. I've solved the problem. So as you can see, that oracle is really great, right? On this math data set, if we get enough generations, typically 1,000 to 10,000, my model has 100% performance. There is always one out of that 100 or 1,000 or 10,000 that is correct. And the oracle tells me which one that is, and I'm good. However, if I do other things, so for example, I could use majority vote in green, or I could use some other techniques like bringing in a reward model, for example. A reward model is the thing that we talked about in RLHF. It's just this model that gives me a single scalar score. Now, our reward models in the past were things like, oh, does the user like this generation versus that one? This time we'll use it directly for verification, so it'll be like, what is the probability that this solution is correct? But it's still the same idea, right? So I can use a reward model, and then I can go ahead and say, hey, go ahead and rank all of these guys and pick out the one of the highest reward, and consider that to be your solution. And notice how big the gap is if you look at this yellow curve versus the blue curve, right? My reward model could not figure out exactly which of my generations were right and which ones were wrong. The solution I got that had the highest reward did not turn out to be correct a lot of the time. In fact, it's something like 65% of the time, the reward model couldn't figure that out. Everybody see what I mean? So I have a correct solution somewhere in my data set of generations that I got, but I don't know which one it is. And by using this reward model, I can pick one out, but it turns out to be the wrong one. It turns out to be incorrect. And in fact, other approaches, I can sort of do combinations of reward models and majority vote and so forth. They're not really much better. There's still this very big gap. And we're seeing that regardless of model type here. OK, so this is sort of the problem of verifiers. Yes, I want to use as much signal as I can. But unfortunately, if I don't have a good verifier, test time scaling kind of doesn't work very well, right? And in fact, you can see that it really flattens out, too. Sometimes it gets worse. I'm not even getting the kind of scaling behavior that I want, where I'm tending toward 100% at some rate. Instead, in this case, I flatten out. I'm getting nothing more from additional generations. So this is the challenge. We're going to need both sufficiently good generators so that they can actually find a solution that's correct, but I also need a good enough verifier that's also going to be able to pick out one of those correct solutions. And if either piece is missing, we're not going to be able to do this test time scaling. Okay, so that's our goal. Let's obtain a verifier that gets as close to the oracle verifier as we can for any case where we don't have access to this oracle. Okay, so how should we do it? Well, basically, we'll build whatever kind of system for my verifier that I can. So one example is I can use a bunch of rules in place. We're kind of doing this, for example, when we do unit tests, right, for my code. I'm trying to say, hey, here's a bunch of things that I need the code to have. Here's a bunch of rules that I'm going to enforce. Or I can do a straightforward program as well. So one kind of classic example of verifier is to say, hey, your output generations should be themselves a program. I'll hook up that program into my system and run a bunch of tests on it. Or I'll verify it in the sense of formal verification or other things. Okay, so this is kind of a classic thing that I can do. Now, a simpler thing, of course, is based on models themselves. So we've actually kind of already done this, right? I can use things like LLM as a judge. It can tell me, hey, I think this is a good generation or not. I can do a reward model. A reward model will give me a score. It'll say, here's a 18% score for this generation, 20% for that generation. I can even start thinking about kind of making reasoning models to be my verifiers as well. So those are called generative verifiers. And by having reasoning on the verifier side as well, I have a better chance of spotting errors, figuring out what is not a good solution. So this is kind of from the paper that introduced generative verifiers. The top thing is typically what we're going to end up seeing when you have simple reward models. They really just produce a single score. And this score is really something like, hey, what's the probability that this whole solution was correct? And here, there's lots of mistakes you can make. So typically what people will do instead is have one of these verifiers that is itself a generative model and itself does reasoning. And it will try to look at every step and try to figure out, is there a mistake anywhere? So fairly simple, right? I'm just going to say, give me another powerful LLM, have it look over every step of the generation, try to pinpoint any issues, and use that as the thing that acts as a verifier. All right, so how can we improve our verifiers in general? Not surprisingly, it's almost exactly the same thing as when we try to improve inference. So whatever maneuver we make on the generator side, we can make the same kind of thing happen on the verifier side. So just to see an example, we can run multiple times on the verifier and aggregate. Everybody see what I mean by that? This is now test time scaling for verification instead of test time scaling for generation. But it's also useful, right? Because again, I really need both of these things to be good. I want my generator to eventually output a correct solution, but I want my verifier to be more and more confident in its verification, which means it's not good just to verify once. I may want to verify 100 times and take a majority, for example, or some other combination of those. Yeah?
So do these verifiers oftentimes, or do people often use teacher-student networks to distill these verifiers? Since like if we're using a big LLM to do this, this just becomes throwing a lot of compute at a problem.
Yes, I have to account for the compute for the verifier side as well. So yes, any trick I have to get more efficient in that sense is good, right? So if I can distill, and we'll see an example coming right up, that's a good thing to do. But yes, you're on the right track there. And yes, we have to consider all of these, right? If I'm going to use a certain number of tokens, I have to think about how to allocate it between generation and verification. It becomes pretty non-trivial. All right, everybody okay with where we're going here? All right, so we decided initially that one answer is not good. Let's increase the number of candidate answers. Then we realized we don't know how to verify those candidate answers. So for each of them, we're going to increase the number of verifications. So that's the current story. It's getting a little bit more complex. But this is what we need to do when things are imperfect, both on the generator and verifier side. OK, so there's a paper called Weaver that came out recently. Full disclosure, I'm a co-author on this one, so I like it for that reason, but also for other reasons. But this is using the idea that we just talked about. Let's go ahead and rather than just say I have one verifier, I run it, that's it, let's try to incorporate multiple weak verifiers into sort of what's a single stronger verifier. So here's what I can get. I can incorporate some LLM as a judge. I can have multiple of those guys. I can get a few reward models, et cetera. I can turn all of these guys into some candidate noisy verification scores. And then I can try to compute from those noisy verification scores one final kind of assessment. Like, is this generation good or is it bad? And it turns out there are some techniques that we can use to infer which of those judges and reward models and all these other weak verifier components, which ones are good and which ones are bad. And we can kind of do this without ground truth, which is nice. But the nice thing about this is it can say, hey, you should upweight some of our weak verifiers. You should downweight other ones. And by doing this, you're kind of getting good information from a lot of different verifiers. And you're getting a much better overall assessment. So that's what you get here. And here's the kind of curve that we've been seeing this whole time. This is exactly test time scaling. You're increasing the number of generations. We're trying to figure out what our success rate is. And we're seeing how it grows as we get more and more generations. That red curve on top is just our oracle again. We're trying to reach that red curve as much as possible. And this technique that we proposed here is the one in blue over there. And notice how much better it is than kind of just doing vanilla majority voting. You're getting something like a 30% boost. But you still have a ways to go, right? Between the blue curve and the oracle, the red one, we still have a good amount of performance to try to get to. Yeah?
I was wondering how you got the weights for weak supervision. Is it obtained when, how is it obtained during training, essentially? Because it has to be initialized with something first, and then it decides what's the optimal weight for rejection or acceptance.
Yeah, so the answer is it comes from a bunch of these weak supervision algorithms. And what they really do is they say, hey, look, give me a bunch of different problems, and let me see how these different weak verifiers behave on them. Let me see which ones agree with each other often, which ones disagree, and where. And from this, it turns out that you can infer a lot about which ones are likely to be good, which ones are likely to be bad. So for example, if I have one of those verifiers, no matter what, it always votes yes on everything. It always says this is a good generation. But other verifiers disagree very often with that. I can probably guess that I have a very bad verifier in that case. I should give it very little weight. Now I can formalize this notion. There are nice algorithms that go executed. In fact, you can prove that if these things have enough independence, then you can get exactly what this is if you see enough unlabeled samples. So the answer is there's a whole theory for this that you can kind of rely on here. It doesn't require any samples, and you do this once during a training phase. So this is not something that you do on the fly, where you try to figure out how much to upweight or downweight for each sample. It's for the whole data set.
So this is similar to how people do qualitative studies, and then they kind of see agreements and then put that through.
Yes.
Oh, okay, I see.
Yeah, so it turns out that if we have 3 independent views of some ground truth that's latent for us, then just from seeing those 3 independent views, I can gauge how often each of their sources is likely to be right. I cannot say where they're right and where they're wrong on any particular sample, but I can say that on average. This is a very beautiful fact that I can show you the proof for, but that's sort of the intuition here. Cool, so this is a nice trick here. We can get some really convenient boosts just by using a bunch of weak verifiers that I combine. And kind of getting back to the point that you made, we can actually distill this entire system into one smaller model. So rather than saying run all the weak verifiers, I can take their outputs and distill them into a smaller verifier model, a single one, that behaves like this aggregate thing. And by doing that, the amount of compute I have to use becomes extremely, extremely small. Instead of running many large LLM as a judge, I run one much smaller model. So you can get huge savings, almost 99%, for example. So this is a good thing, right? Because this is exactly the problem we were talking about. If we're trying to scale up compute both for generations and for verification, we're going to get in trouble, right? Especially because I run the verifier multiple times over each generation. So now I have to find some ways to get cheaper, and this distillation idea is very, very helpful. OK, everybody OK with this? I guess this is maybe the most sophisticated thing we'll have to talk about in this class, right? Test time scaling, which has multiple techniques for both the generator and verifier and so forth. Any questions? And folks can mention if they're confused. OK, I'll assume we're good. So other things about these verification dynamics that we just talked about, right? So we always have this question of, well, what kind of model should I use for LLM as a judge, or more broadly for verification? Should it be bigger? Should it be more powerful than the generator? Should it be different, right? Those kinds of questions. There is no simple right answer, but there's some nice studies that are trying to tackle this question. So here's a paper where they actually went and they kind of tuned both of these knobs. So swap out a bunch of different generators. So try smaller and bigger models, more specialized models, whatever. And then similarly, go swap out generators as well. And try to look at what that combination looks like and see what you get as a result. And all of this is very problem specific, right? So if the problems are sufficiently hard, I kind of need both a good enough generator and a good enough verifier. But in some ranges, the first thing I have to care about more is the generator. And in some other problem ranges, then it's really the verifier that matters a lot more. So you can get kind of a bunch of interesting curves that are telling you a lot about what's going on here. So this is actually something that's pretty interesting. These blue curves that you're seeing over here, this is a plot that's looking at how big, how powerful is the verifier versus accuracy. And it's showing you for different problems. And these problems are at different difficulties. And the thing that's interesting here is, and maybe it's not too surprising, basically what happens is for some problems that are easy enough, you don't really need to keep increasing your generator. For some problems that are hard enough, then, well, there's not much you can do if your verifier. You're just kind of stuck with it. And if you keep making it larger, it's not going to do anything better for you. So you can kind of reverse engineer what is the right allocation of compute to your generator and verifier by figuring out kind of how hard your problems are. All right, so that's all I wanted to say on the verifier side. This is still kind of a nice art that we're doing. It's not fully systematic yet. But there's one sort of further problem. We've been talking entirely about, well, can I verify my solution is correct? But that's not really sufficient, right? If we're doing RLVR, for example, then great. This is all I need is a verifier. But of course, typically, if I am building a system, even if I'm trying to have good reasoning capabilities, I also want other things. So I want some notion of quality to be involved there. And we are used to this kind of concept, right? We talked about RLHF. We were trying to do it there. But for RLHF, we weren't really interested in sort of evaluating in general. We were just trying to build a reward model for reinforcement learning. So it was still a training kind of idea. What if we want to just look at how good our system's doing for evaluation? In that case, we'll use this tool called a rubric. It's exactly what it sounds like. I'll create a bunch of criteria, and I'll try to go ahead and score my generation against these criteria. So we're doing kind of the thing that's orthogonal to verifiers. Previously, we said, hey, well, I want to get the correct answer. Use any tool whatsoever to verify that we got that correct answer. Now I'll do kind of the opposite, which is to say, hey, do I have all of these nice properties I'm looking for in my solution? All right, everybody OK with this? Cool. So let's go ahead and look at what these rubrics will typically look like. You want to create something that's very multidimensional. Again, we're not necessarily going to fine-tune on just one single number, so I can afford to have a bunch of different axes to look at my quality. So again, the opposite of verification, where I really did want to have one number that I can put back into RL. So let's suppose now that I look at my solutions and I say, hey, are they clear? Give me some score on this clarity axis. Are they factual, right? Do they make any factual errors? Do they produce, safe results? So for example, if I have an AI system that tries to answer people's health concerns, is it going to tell them something really bad, like go drink bleach or what have you, right? Which unfortunately, these things have happened, so it's a real concern. So yeah, I'll need to have a rubric that has all of the criteria that I want my model to go ahead and pass. And I need some information about what I'm asking to have verified on this set of criteria. So no more single score metrics, because that's not what we're looking for. Instead, we get very rich feedback. We know a lot about our generations. And conveniently, we can go back and tune against anything that we're doing poorly on. So for example, if it turns out that our generations are really great, but they have a couple of hallucinations in there, they have non-factual aspects, then I know that I should go back and improve the factuality of my model. So these things are very, very powerful, and any modern eval system is really going to have tons of very rich rubrics. OK, now this idea is actually not super new. So there's this system called Prometheus that was introduced a couple of years ago. I believe they formed a company out of this, actually. Basically, they said, hey, well, if I just create rubrics and ask LLM as a judge systems out of the box to score my model and my generations against that rubric, it doesn't work super, super well. So they had this idea of, let's just fine-tune a model that's very good at producing rubric results. So they said, hey, take in a bunch of different instruction sets, eval sets, and go ahead and say, hey, this is what the rubric should look like when I manually do it, and fine-tune a model that becomes very good at this. So they have this sort of specialized model that is really tuned to be a good evaluator along a bunch of different axes, actually thousands of different axes. I don't think anybody's actually using this model or really this company, but the idea in general makes sense, and it's been adopted by a lot of people. I do want to show one example, and unfortunately we're running out of time. So HealthBench is a very large new benchmark, specifically for these kinds of health applications, that OpenAI released this summer. It is also rubric-based, and it's actually huge. So they have 5,000 health conversations. So this would be like a patient speaking to a model to get medical advice from that model. So high stakes, again, you cannot have your model make mistakes here. That would be a disaster. And they have a huge number of rubric criteria, about 50,000. So as you can see, that's something that's enormous. And the reason for this is because actually they have a ton of them for each of these conversations. So it's not a single rubric that applies to all of the data points. It's actually rubrics that are customized for every single data point, which is normal, right? So when you think about a conversation of multiple turns, a lot of the criteria for what's good kind of pertain to that conversation rather than being something you can generically apply to everything. So this is actually quite nice. You can see some examples. I've just highlighted a few here, right? So for example, the basic story is, okay, I found my 70-year-old neighbor lying on the floor unresponsive. You know, it's stuff like that. The model will say, hey, I'm not your neighbor's doctor, but here's what I think you should do, which is typically what you kind of want to see from these models. And then we have all of these criteria in our rubric. This is just the first three, but there's a ton more. It's like, hey, do I have concise advice to call emergency services? If that's present, you get 10 points, right? It's exactly like grading some student's exam. I have all my criteria in my rubric. I have different amounts of points for each one, and I add up my model's performance for each of my data points. So very powerful, because it gives you a very rich amount of information about what the model's doing. Very expensive to generate these rubrics, though, right? A lot of manual human creation in it. So it's kind of like going back to when we talked about metrics, and we said there's a lot of custom metrics. Now we have vast numbers of custom metrics that all get wrapped into this rubric concept. And what you can do is kind of group all of these together, and then you can kind of look at, well, how good are different models along a bunch of different axes, right? Are they good at suggesting emergency referrals when necessary? Are they good at asking for more context when they should, et cetera? And you get this kind of pretty good assessment about different models. You can compare cross-model, but you can also look within a single model how well they do across each of these axes. It's a very, very powerful concept. We'll talk more about this and multimodal stuff next time. Unfortunately, we ran out of time. All right, everybody submit your presentation stuff and come chat in office hours this afternoon.
Question about the rubrics.
Yeah.
So, for example, like emergency referrals, are those just program-based verifiers?
No, there are other elements. Element of the judge usually.
Oh,
It's too hard to implement programs typically for every single criteria. So you get lazy. You do element of judge on edge, and that increases noise, right, in your evaluation, unfortunately.
Yeah.
But it's cheap and easy.
what if it's just an actual medics? Well, I mean, we can't do emergency referrals, right? But like clarity, safety, we have a good understanding.
There are, right? So there are explicit models such as correctly assessed. That's closer to the reward model concept, right? Like a supervised model that gives you a score for safety. Those exist and people use them all the time. You can incorporate those into your rubric if you want to. But unfortunately, the thing is, like, you're now creating systems with lots of different parts, whereas people have very simple systems that just say, okay, I use LLM as a judge against every one of these textual criteria. The end. That's much more common, unfortunately, even though it's worse.
judge.
Well, the simplest thing you do is kind of what we talked about. You say, oh, I'm going to do 100 experts for each of my rubric criteria for a handful of points. Get some performance from that, correlate it to LLM as a judge. Correlation looks good. I just trust LLM as a judge for everything else. So that's even more expensive, right? And it's not always totally reliable because correlations can be too. But it gives you some signal, right, that you're doing the right thing.
That's why we're betting a lot on the smaller models.
No, I think that's
Rubric based, like we have to be way better if we just have small models that specialize in just like judge this, that's it.
Yeah, so that's that Prometheus idea. That's basically what they were trying to do. Ironically, no, we ended up using the most powerful model, right? Now, okay, we use the most powerful model, but typically we got too much reasoning. So we'll use things like GPT-4o, which is a very good model, but it doesn't have reasoning. But it's both cheap, fast, and pretty reliable for things like rubric scoring. So things like that. Yeah, it's actually not the cheapest. Yeah, so for a lot of like new benchmarks, just to introduce a new model and go test it and get the scores, it can cost $1,000 or more. I mean, it's not crazy or anything, but like, yes, it's a real spend.
Got it. Thank you.
Yep.
Hey, just to be clear, you said submit the project stuff or
Presentation.
proposal
Yep,
stuff?
like just tell me which paper you're doing. That's pretty much it.
Thanks so much.
Someone forgot their.
Oh, shoot.
Brendan said that he sits the guy next to him, which goes to office hours. I don't know if you want to bring it or I guess just
I
leave
can
it
take
here.
it. Yeah, sure. Let me actually just make a post as well.